Okay, continuing on with confidence intervals. Again, now we are in this phase of where we have a confidence interval that is more practical because sigma is unknown, all right? And, or at least it's unknown in our, it's unknown in most situations, but in terms of our formula, we're treating it as unknown. This is a more practical confidence interval. And in this scenario, there's two types of intervals that we will consider. One, where the sample size is large, that is, where n is at least 30, bigger than or equal to 30. And the other is when the sample size is small, that is, n is less than 30. And this may remind you of the central limit theorem. That was kind of the threshold we set for invoking the central limit theorem. Those two scenarios, large sample size, small sample size, but in the second scenario there, the data comes from a normal, let's see if I can write this, a normal or a near normal population. Okay, scenario one, a large sample size. The conditions here to use this formula are that we have a random sample, that our sample size is bigger than or equal to 30, that sigma is known, sigma is unknown. That's the more practical setting. Those three conditions allow us to use this interval formula here. Ultimately, what I want you to focus on is, yes, here's our lower bound and upper bound, but this is the compact way to represent that interval formula. So we would compute that, and if you look at it, the structure is the same as the one we had before, but instead we have replaced sigma with S. S is the sample standard deviation. Okay, so S is the sample standard deviation, something we can actually find, and we are going to use that in this confidence interval formula. So the derivation of this interval, we did this before for that first confidence interval. The question there was, how does one come up with the endpoints for the interval? Well, how does that happen here? It turns out it's a result of this sampling distribution. It turns out that x bar minus mu over s over root n is approximately standard normal for large, quote unquote, that is where n is at least 30, for large sample sizes, and that's by the central limit theorem. The central limit theorem is driving the result that this ratio here follows an approximate standard normal distribution. And so if we know that, what we can do is, scroll back here a couple of pages, we can have statements that are statements similar to this, but we replace sigma with S, and then we would have the development that would start off here, or really the line above. We would have S in there, and then you would solve for mu, and you get the same structure, except you've got an S here and an S there. Okay, so let's see. So that sampling distribution of x bar minus mu over S over root n is driving the foundation, the derivation point for the confidence interval here. Now, this is the large sample size scenario. All right, we're going to get to the second scenario where the sample size is small, but in order to use that scenario, we need to develop a new probability distribution. And that new distribution for us is called the student's t distribution. And so here I have the probability density function of a student's t distribution. This is a continuous distribution. And when you look at it, I mean, just this PDF, if you thought the PDF for the normal distribution was a mess, this is really a mess. This Fortunately for us, we're not going to use this formula at all. I just wanted you to see that here is the function, and when it is plotted, you get it has a picture, it has a shape that looks a lot like the normal. Down here you can see it. It's bell-shaped and so forth. But let me come back to this, at least say one thing about the density here. There's some mathematical terms in here. It involves this thing called an integral. For this class, we're not worried about that. But I just want to focus in on one thing about the, let me go to the pen. I want us to focus on one thing about this distribution called the degrees of freedom. Okay, that's a parameter within this t distribution, and we're using this notation. That's a Greek letter nu for that quantity degrees of freedom. So it's kind of like looks kind of like a V, but it's the Greek letter nu. And here's a picture. This picture's from Wikipedia. And what I've got here, if you look at the plot, and from Wikipedia was calling K the degrees of freedom here. So for us, nu would actually be the K values as they're listed here. But if nu is 1, we have this. We have the black plot. If nu is 2, we have the blue plot. If nu is 5, we have the green plot, and so forth. It turns out a couple of things. So as the degrees of freedom gets bigger, the peak starts to come down and the tails start to tighten up. Okay, actually, let me back up. I said that wrong. As the degrees of freedom gets bigger, the peak goes up and the tails start to tighten down. Okay. You see that as you go from 1 to 2 to 5 to 10. And then if we let K approach infinity, we get this pink plot. And actually that pink plot is the standard normal. So that top plot there is the standard normal plot that we've seen before. And so what we see is this t distribution is very closely related to the standard normal distribution. So looking at this, and I'll make that clear, we're going to use this distribution a lot in this course. It's very similar to the standard normal distribution, but it has heavier tails. Okay? It has heavier tails. And you can see that the pink distribution, the tails are smaller than these other distributions, say the green one. You can see that pretty well. If I pick a point, say like right there, the area under the curve to the left of that point for the green curve is much bigger than it is for the pink curve. Okay. All right. And also, let's see here. As nu, or as the degrees of freedom approaches infinity, or as the degrees of freedom gets larger, the t distribution approaches the standard. This is actually the standard normal distribution. Okay. So we see that from the plot. A couple of other facts here. One is that the mean of the t distribution is 0, and you can kind of see that here. You would balance this distribution at 0. The variance turns out to be this quantity here, nu over nu minus 2. We're not going to appeal to these facts really really at all in this class. I'll appeal to the fact that the mean is 0, but not to what the variance might be. Okay, but I just want you to be aware of that. All right, just be mindful of it. Just show it to you. The usual source of a t distribution. Okay, where does this sort of thing come from? The usual source is when we're taking a sample from a normal population, and it would look like this. If x1, x2, all the way up to xn if that is, let's see if I can get the pen to write here, is a random sample, from a normal distribution. In this case, it's a normal distribution where the mean is mu and the standard deviation is sigma. Then the quantity t, which is defined to be x bar minus mu over s over root n, follows a student's t distribution with n minus 1 degrees of freedom for any sample size n. Okay, so basically if we take a random sample from a normal population, this ratio follows a t distribution. Okay, so this result here does not have a large sample size requirement. If we go back to the situation where we saw that this quantity here followed a approximate standard normal distribution for large n, the CLT drove that result. Well, it turns out that ratio that I've got circled there does not follow a normal and is not really that close to a standard normal if n is small. Alright, and n comes from any population. But along came a fellow named William Gossett, and he demonstrated that, well, if the x's come from a normal population, no matter the sample size, then let me take that off, then this ratio, it's the same kind of ratio, but it follows an exact t distribution. And for some reason this did not pick up, or I didn't write it, but the degrees of freedom is n minus 1. Now for us and the t distribution, we are not too concerned with modeling using the t distribution. That is, I'm not that interested in assuming some variable follows a t distribution, then I ask questions about its the probability of seeing something larger than that variable, the particular values of that variable, and this sort of thing. We did that with the normal distribution. We modeled IQ scores with a normal distribution. That kind of modeling procedure is not done typically with the t distribution. What we want to do is we're going to use its percentiles. When it comes down to it, we're going to use its percentiles because that's the distribution of this ratio here. So the percentiles, the notation for that would be as follows. If we've got a 1 minus alpha percentile of a t distribution with degrees of freedom nu, that notation looks like this: t subscript nu, comma, alpha. Okay, and in terms of where that is on the t distribution, remember the t is bell-shaped just like the normal, centered at 0. This is a t value. Degrees of freedom is entered first there, and then alpha here is next. But it's the t value such that the area under the curve to the right, is alpha here. Okay, so that's what we're going to be interested in with this t distribution. Alright, that was an aside. Now let's come back to confidence intervals. Back to confidence interval on a population mean, where the standard deviation of the population is unknown. Scenario 2 here, the small sample scenario, we have a random sample. We have any size sample. It doesn't have to be large, but we need our population to be normal, or at least close to normal. And our standard deviation is unknown here, that more practical situation. The normality assumption in this case can be checked by looking at the histogram of the data. And if the histogram is close to bell-shaped, then normality is the assumption of normality is defendable. You can look at the histogram, or really I prefer to look at the QQ plot. Okay, if the QQ plot is fairly linear, also called the normal probability plot, then the normality assumption is tenable or is defendable. The histogram is not not very reflective of the underlying distribution if the sample size is small, but the QQ plot can give us more information about departures from normality if we have a nonlinear QQ plot. Okay, so the confidence interval, what does it look like? Well, it's going to involve this t distribution, and the first thing you're going to need to find is this t sub alpha over 2. So, let's see here. See, I've kind of lost my, whoa. I need to go way back. All right. Sorry about that. Technology sometimes can be great. Sometimes it can do that sort of thing. Okay. We want this t value. Okay, this is a t percentile. It looks a lot like the standard normal percentile, the z percentile that we had before. Our degrees of freedom is n-1 still. The confidence interval, when you look at the formula, I mean, it looks a lot like the formula that we just presented. The only difference here is the z percentile was replaced with the t. Okay, and so once you know how to do one, the other's very similar, but you need to use the t distribution table to find these t percentiles. Okay, derivation of the confidence interval. Where do these endpoints come from? So I'm going to ask this question again. It turns out it's a result of the sampling distribution of this ratio. X bar minus mu over S over root n is distributed as a t distribution if our population is normal. Okay. And that's what this whole usual source of the t distribution was about. It told us how to generate a variable that follows a t distribution. Okay, if that condition is satisfied in the first line there, then we have that ratio that follows a t distribution. And so we set up a probability statement similar to the very first one we looked at several pages ago in deriving the confidence interval for mu for the first time. And instead of z percentiles, we're going to have t percentiles in the picture, but you get the basic structure is the same. Okay, here's an example. Take a moment, read this example. You may want to hit the pause button. Okay, upon reading this example, you will see that we are interested in estimating this parameter, the mean serum level of vitamin E in all persons similar to those in the control group. So this quantity was of interest in this study here, so we want to estimate that with a confidence interval here. All right, so it seems like that has happened again. All right. This is what we're after. This quantity is mu. It's defined, that's the parameter of interest. And as you look through this setup here, you may wonder, well, what interval formula should we use? Well, we should use the one that coincides with the large sample size situation. So we're going to use this formula here, x bar plus or minus z times s over root n, because n is large. All right. Now, n is large. We also have a random sample, and the standard deviation of the population is is unknown. Okay, but what would we plug in where? Well, the sample mean here, what was the sample mean? The mean serum level from the sample was 11.9. Plus or minus, what's my z-value? I've got a 95% confidence interval. I'll let you verify this, but that turns out to be 1.96. That's the z-value for that confidence level. And then S, the standard deviation of the sample. Notice that's 4.3. Okay. Then divide by root n. Let's see, the square root of 96 there. Okay, so I'll let you work through that computation, but that's just illustrating the use of this kind of interval, the large sample confidence interval on mu. Okay, another example here. Take a minute, read this all the way up to those plots there. Okay, so here's a situation with real data, okay, from a study, and it's actually taken out of we have a case study manual for our undergraduate statistics course. This data comes from that case study manual, looking at pulse wave velocity measurements. And of interest, we want to estimate the average pulse wave velocity, okay, for children with HGPS. As this pulse wave velocity tells us something about the thickening of the artery walls and general cardiovascular health. So this is of interest to the researchers, and statistics can play a role here. Here's the data. There's 18 data points from 7.2 all the way up to 18.8. You can see the data is ordered. And what I did was I did some basic summary statistics in JMP. And first we can notice here that within JMP, the sample mean was 12.4 and the standard deviation was 3.64. If you want to look at the quantiles, you certainly can. Here is Q1 is 8.9, Q3 is 15.1, the median was 12.9. In terms of putting a picture to the quantiles, the box plot does that well for us, and here's a picture of the box plot there. That's done in JMP, and also within JMP is this histogram. Now, when you look at the histogram, there's only 18 data points. It's somewhat believable that this data could come from a near normal population. There's not just a lot of strong evidence against normality. I know this bar here is low, but if the class widths were adjusted slightly, then we might get a different kind of picture. But there's that general kind of bell-shaped curve to it. But I really like to look at the QQ plot anyway. Here's the QQ plot in JMP, and the data, while it's not going to fall perfectly on a line, that's not realistic, it's pretty close to that line, and nothing is falling outside of those bands. And for us from JMP, that allows us to reasonably make the normality assumption. Okay, so we have all this information, and that's JMP has done that descriptive statistics for us. All right, so going on to answering some questions here. What is the parameter of interest? Well, it's mu, and that is the mean or the average pulse wave velocity for all children with HGPS. Okay, that's the thing we want to say something about. There are several thousand in the world that have this syndrome, and we are only looking at 18, and we want to use the 18 to try to say something about the average of all the children here. Okay, and so There is a question of is this sample representative of the entire population? You know, you'd have to go further back into the study to answer that question, and maybe even talk to the researchers to see how they got these 18 children. But we're going to assume that it's a representative sample, that it's a random sample for us, and that we're good to go with using this to do our confidence interval here. So we're going to compute a confidence interval for mu, and we're going to use, let me write this out here, we will use x bar plus or minus t sub alpha over 2 times s over root n, and we use that because our sample seems to have come from a near normal population per the QQ plot. Okay, that's the main assumption that you need to check in using this interval here. Okay, and we can review the other assumptions. So coming back here, what were the other assumptions? We needed a random sample, any size sample. Our sample is random here. We're going to assume the researchers got it in that way. Any size sample, we're okay there, and sigma is unknown. We have not assumed knowledge of the population standard deviation. So we're going to go forward with this interval here, plugging in the appropriate values. X bar, that's the sample mean here, right? This is X bar, and this is S. Okay, the sample mean is 12.44 plus or minus. Now I got to plug in my t value. If you look up on your t distribution table, a t distribution here, the degrees of freedom is n minus 1. In this case, that's going to be 17. If you look up the upper 97.5th percentile, you're going to get 2.1098 for that t percentile. Then times s, which is 3.64, rounding, and divided by the square root of 18. That's going to be the values you plug in there. Do a little simplification. We get 12.44 plus or minus this. The arithmetic here yields 1.81, and ultimately a lower bound of 10.63, comma 14.25. Okay, so what does that say? Well, that says the interpretation would be we are 95% confident that mu, that is the average pulse wave velocity for children with HGPS, is between 10.63 and 14.25. Okay, and it turns out that the little bit I know in regarding pulse wave velocity measurements, that if the value is, is upwards of 6 or 7, that's considered high, and so the average pulse wave velocity for these children seems to be really high, which coincides with the thickening of the artery walls, and so that might suggest treatment for their heart and for the thickening of the artery walls. Okay, continuing on here, we have this situation. Again, we've seen this sort of thing before, a sample size determination. The motivating question here is I want to take a sample. I have yet to take a sample, and I want to a confidence interval of a particular width. How large should my sample size be? Similar to what we saw before, we're going to have this sort of thing. Z times S over E quantity squared would give me the sample size. The only thing that's different now is I've replaced sigma with S from before. So I've got this sample standard deviation, so that seems reasonable here, but we haven't taken a sample yet. So what do we plug in for S? Right? We have yet to take a sample, so we don't have a sample standard deviation. Well, typically what's done is you plug in a value for S that has been determined by a pilot study, that is a smaller study before the main study. Or maybe you use past data to get a sense of what S would be. Another approach, and a pretty clever approach, is to take the projected max and projected min of your data set and say that, well, the sample standard deviation is going to be pretty close to the max minus the min over divided by 6. Okay, so why is that the case? This actually comes from, so think back with me, empirical rule idea. Empirical rule said if I have a bell-shaped distribution and I'm sitting at mu, and I go out to mu plus 3 sigma and mu minus 3 sigma, that I'm going to get almost 100% of the data in between those two values there. And so really probably the tail would actually be closer to the axis here. But the point of what I'm getting at is that there's 3 standard deviations going from mu to mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. There's 3 standard deviations to go from mu to mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. So there's 6 chunks there. And if I treat this as a practical max and this as a practical min, the difference between those two divided by 6 will give me a good sense of what the standard deviation would be. Okay? Now it's not a perfect approach, but it's a approach that can be used here. All right, another example. A student in public administration. Take a minute, read this. Hit the pause button. So after reading through here, you're going to notice that you're going to use this formula to get the required sample size. Z sub 0.05 over 2 times S. That's a S, not a 5, it's an S. Divided by E, quantity squared. Okay, that Z value is 1.96. I've got a 95% confidence interval. S here is estimated from a pilot study, or in this case, I'm sorry, a past study. The past study suggested a standard deviation of 1,000. Okay, so we didn't actually have to use this particular technique up here. So 1.96 times 1,000 over E. E is the E here is the half width of my interval. So what do I have? The 95% confidence interval estimate should be no wider than $200. So the interval should not be wider than 200. That means E needs to be 100. I'm going to square that, and then let's see what we get if we square 1.96 times 1,000 divided by 100. You're going to get roughly 384.16, and so you'll want to round up to 385 should be your sample size. Okay. If you wanted a 99% confidence interval, then the actual sample size needed would go up considerably, and if we bump up, yes, this confidence level up to 99%, the required sample size goes up to 664. You can work through that, but to get just 4% more in your confidence, you've got to get a lot more data points, almost twice as many. So sometimes it's not worth it to get that much data if the data collection scheme is expensive. All right, so that wraps up sample size determination for a population mean in terms of interval estimation. This next section is hypothesis testing, and we'll see that in the next video.